In an election year, people might disagree about who makes the best candidate, but you don't hear much argument on the merits of democracy, that millions of average people can together make a wise decision. It wasn't always so. In the early 20th century, this controversial Englishman, Sir Francis Galton, tried to statistically test whether mobs of common folk were capable of choosing well. And, as our musical correspondent Rob Morseberger tells us, what Sir Francis actually found was that, mathematically at least, there's often wisdom in a crowd.
Sir Francis Galton was a nobleman and scorned the common masses. He thought that votes of governance should be left to higher classes. He'd prove with all the data from a contest inescapable of guessing even simple things the commoners were incapable.
Ladies and gentlemen, step right up.
What kind of contest might it be?
Guess the ox's weight and see. Guess the weight correctly and win a prize.
It's 100.
Said a little one.
That's much too light. At least a ton.
An eager crowd queued up to play. 800 made a guess that day.
So we had 800 data points.
And now the ox's weight is exactly 1,198 pounds. There are no winners.
Sir Francis knew the rabble would never guess the weight. How might they judge important things if left to meet that fate? With mathematics, he would show how far they went astray. But in the end, his theory was in total disarray. Because a curve of all the guesses.
Oh, that curve? It's the cumulative distribution function of the normal distribution. Sorry, that's what it's called.
Because graphing all the guesses and determining their mean.
I think he was talking about the median.
And determining their median, he showed that if the crowd were one, its estimate is keen. He showed that if the crowd were one, its estimate is keen.
Keen, yes.
That's because while no individual guessed the actual weight, the average of all the guesses is exactly right.
The average will generally be better than a randomly selected individual guess.
The average of the masses assures us of success.
I think he was talking about the median.
And the larger the number of guesses we toss in,
The more likely we are to get the right answer about the oxen.
this premature prognostication, they cannot help but scoff.
Galton should have gathered more data before he went shooting his mouth off.
Sir Francis's hypothesis was rocked by ignoramuses. He lost the proof he had avowed. He found the wisdom of the crowds.
If you have a group of people and they each have tiny bits of information, then you can learn a lot if we could just gather all of those bits together.
It's just like Wikipedia.
Well, this isn't exactly like Wikipedia, no. It's a little bit different.
It could maybe be Wikipedia. You don't even need to be an expert, but if you know something, then you're able to contribute, and that entry is able to be that much more informed.
Another sample of this fair?
Who wants to be a millionaire?
Yeah, the audience lifeline.
If a person feels like they can't answer the question by themselves, ask the audience.
The audience is right over 90% of the time.
There you go.
How about that, Gelman?
The wrong Gelman.
Sorry.
One by one, we're not too smart, but every guess, it plays its part. And when you add them up, you'll find the wisdom of the crowd.
And that is the wisdom of the crowds. So let me summarize this again. So what had happened? So basically this guy, Francis Galton, who actually was a cousin of Charles Darwin, he visited this livestock fair and he came across that contest where everybody was asked to give a guess and make an estimate about the weight of an ox. And Galton, he disliked the idea of democracy to begin with. You know, he thought it's like a stupid idea to give everybody a say in something that they are no experts in. So in the days he thought, the government should be run by experts, or actually the government should even be selected by people who know what they are doing, not by everybody. Back to this competition, there was an ox on display, and people could give their guess about the weight of that ox. And there were around 800 people who made a guess. Some of those were experts, others were farmers or butchers, and yet others had no idea about the weight of an ox. What is the weight of an ox? I have no idea. Is it 50 kilograms, 100, 500, 2,000, 5,000? I have no idea. So Galton collected these individual guesses after the competition was over. And then he took all those guesses and he calculated the median. Median is really just the halfway point, like 50% of the guesses were below and 50% of the guesses were above. That's the median. The median was 1,207 pounds. And now it gets spooky. Because the correct weight of that ox was 1,198 pounds. That's incredibly close. That's just 9 pounds off. That's just 4.5 kilos off on an ox that weighs around 600 kilograms. Just 4 kilos off, that's pretty good. Not even speaking about the general weight of an ox, but that was the weight of that particular ox. It is a very cool study, so I thought, let's replicate this. Let's do this in the class, and I did. So I showed undergraduate students in Dublin the picture of Penelope. That's Penelope up there. I know her, and I asked students to give me the weight of that cow, their best guess of the weight of that cow in kilograms. So it turns out the average guess of the male students was 608 kilos, and the average guess of the female students was 408 kilos. Interesting that there is a difference to begin with, but that's another thing. The overall guess was 474 kilos. The true weight of Penelope was 615 kilos. So again, it was actually pretty close when you think about it. And if I would ask you what is the weight of that cow, you would have not guessed that we get that close to it. So other people also replicated this experiment. As a podcast, I'm going to link to it, where they had over 17,000 people participate in it. So over 17,000 people gave their best guess of the weight of Penelope. And as it turns out, again, they were incredibly, incredibly close. So their average guess was 1,287 pounds, while the true weight of Penelope is 1,355 pounds, which is around 615 kilograms. In a normal year, I would also do another experiment with you guys. So I would come along to class and bring this jar of candy. And I would hold it up and I would ask you to tell me how many candies are in that jar. And the average guess that my students gave me was 69.3. So all guesses together, the average 69.3. And then we went and counted it in the class. Everybody picked a candy, and at the end we knew how many candies there were in the jar. As it turns out, there were exactly 69 candies in the jar. So the average guess was 69.3, and the true number was 69. That's pretty astonishing. That's just mind-blowing. So James Rebecki, he wrote this book, The Wisdom of Crowds, and you guys had to read a chapter out of that. And in that book, he says that under the right circumstances, groups are remarkably intelligent and are often smarter than the smartest people in them. Groups do not need to be dominated by exceptionally intelligent people in order to be smart. Even if most of the people within a group are not especially well informed or rational, it can still reach a collectively wise decision. So he's saying that groups can be smarter than the smartest people in these groups. It's a very interesting read. The book reads very easily. I can recommend it. Another instance where you might have come across the wisdom of the crowd effect is the game show Who Wants to Be a Millionaire? Okay, so in this game show, people get asked questions. They have to choose A, B, C, or D, and there are also a couple of lifelines. Yeah, so if you don't know the answer, you can phone a friend. And looking at all data, other people did that. Looking at all data of those shows, the friend is right in about 65% of the cases. You could also, as another lifeline, ask the audience. Yeah, so then the audience, they have a little tool where they choose A, B, C, or D, and so the audience makes their choice A, B, C, or D, and you see the distribution of choices that the audience made. As it turns out, the audience is right in over 90% of the times. Maybe you have wondered about why is it that the audience always seems to get the question correct, even though it might be a very difficult question. Well, the answer is the wisdom of the crowd. So what I'm going to do now, I'm going to play with you a special edition of Who Wants to Be the Millionaire to demonstrate the wisdom of the crowd effect. What was the true weight of the ox in Francis Galton's Wisdom of the Crowd study? Was it 598 pounds? Was it 712 pounds? Was it 1,198 pounds? Or was it 2,398 pounds? That's the question. Well, that is funny. So now I'm here, now you see me from another side. But let's play this game. So imagine you come along and you remember, it was something with 98. So you might not know whether it was A, C, or D, but you're pretty sure that it wasn't B, 712 pounds. So you don't know, you randomly choose from A, C, or D. Now let's imagine somebody else who knows that it definitely was above 1,000 pounds. Can't remember which one, but randomly choose between C 1,198 and D 2,398. Now imagine another person who might think that, okay, well, I've no real idea about the weight of an ox, but 2,398 sounds too much. So let me randomly choose from A, B, or C. Okay, now another person comes along and thinks, well, 500 sounds a little low, 2,000 sounds a little high, so I think it was in the middle. I have no idea, but it's either B or C. So randomly choose B or C. And maybe you see what's happening already. None of these people knew the right answer, but collectively, we seem to be getting it right with zoning in on C. And as it turns out, C is the right answer, 1,198 pounds. So none of us knew the right answer, but each one of us partially contributed something. Yeah? It might have only been knowing that it wasn't D, or maybe somebody else knew, well, it probably wasn't A or D. So nobody needs to know the correct answer, but still, collectively, if all of us add little pieces of information, collectively we can come up with C, the right answer. Let me talk about another paper where this phenomena was studied a little more, a paper by Hong and Page, published on the Proceedings of the National Academy of Sciences, and this is one of those papers that, if you're master students, it could be very interesting to replicate that model and then extend it. Yeah, replicate it and extend it. I have a couple of ideas in that regard. So basically they have a very abstract model, and a very abstract model where they think about how do people solve problems. And they kind of set up this artificial world, where people have different heuristics, and that means different things that they can do. So imagine we have a world with different solutions to problems, and they are now reflected here in this circle, and each number in those circles reflects the quality of a solution. So how good is it? So the higher the number, the better is the solution to a problem. And now we have heuristics, and we have different individuals that can do different things. So now let's look at different people. So we have a gray person, and that person brings something to the table for solving that problem, like a different strategy, a different way of going about solving a problem. And here it's represented in an abstract way by that gray individual being able to take 4 steps once, right? So we start all on the top with the solution that is shitty, 2 is a very low value, and the gray individual can take 4 steps. That's all that individual can do, right? Okay. So when we look at that, well, that's actually the best solution. So that's a really good solution. 81 is higher than what the gray individual could have done before. Imagine that individual can only take 4 steps once. So from 2, taking 4 steps, end up with 81. Now let's look at another individual. So this red individual has now a different heuristic. So that means that individual brings something else to the table for solving that problem. Like a different way of going about it. And the heuristic that the red individual brings is taking 9 steps multiple times. What does that mean? 9 steps starting from 2, that individual would end up with 16. And then that red individual can take another 9 steps, would end up with 2 again at the very top. So what is the best solution that that red individual can come up with this heuristic of taking 9 steps multiple times? Well, the best solution is at the bottom, 16. Now let's look at a third individual, a green individual who brings the heuristic to take 6 steps at once multiple times. So that individual starts with 2 again, can reach 18, but then also 66. And then that individual would be at the top again at 2. That's really just a simplification of what that green individual brings to the table for solving this problem. And the best solution that the green individual can come up with is 66. So when we compare these 3 different individuals, with their different heuristics that they brought to the table, all started at the top, the gray individual came up with the best solution, 81. While the red individual individually could only reach a solution with a value of 16, and the green individual could only reach a solution with a value of 66. So it seems to be the gray individual would be the best individual here. That's the best solution that we can come up with. But now let's bring the crowd in. And now instead of looking at them separately, now let's combine these heuristics for the red and the green individual. So basically, now we put them together and they both bring different things to the table to solve this problem. The red individual can take 9 steps and the green individual can take 6 steps. So now we have, collectively, they can do both of these activities. And you see already how this is unfolding. Now they have more solutions that they can reach. And in fact, their best solution of this combination of taking 9 and 6 steps repeatedly, many times, you can walk around, these are all the solutions that they can reach. The best solution that the red and the green individual can come up with together, combined, is 91. And 91, it's pretty high. So 91 is higher than all the solutions that those 3 individuals could have come up with individually just by themselves. So it's higher than the best solution than what they could have come up with. So this is one of those examples, where 2 individuals that are not that great in solving a problem combined can come up with something, with a solution to a problem that is better than what the smartest person in the group could have come up with in the first instance just by him or herself. I know this is a bit abstract, but it is a cool paper. It kind of shows you how different heuristics and combining different heuristics can lead to a solution that is better than what individuals could have come up with just by themselves. So the wisdom of the crowds. It's a fascinating phenomenon. You know, when you read a little more about it and think about it, it really is very intriguing. For us, it is interesting for the following reason, because we might know things about individuals, we might know everything about those individuals, but I just showed you that this doesn't mean that we know what they collectively come up with. So we need to think about the different levels, and that's what we do in sociology. We think about the micro and the macro level, and we really need to spend more time in how we get from the one to the other and how we link these different levels with each other. So much about the wisdom of the crowds.
Oh.